Good morning and thank you. Like you said, I'm Johnny Seals from Rice University. I think what I'd like to do is begin by reminding that planetary habitability is something that is dynamic. It depends both on on two energy sources. One is the star, another is internal energy. It's the second source that I would like to focus on during my talk today. This source is important as it helps us to understand how the internal dynamics of a planet can change through time. And specifically, I would like to look at how Earth has changed through time, because that's important to give us an estimate of the types of fluxes that have moved from the interior to the surface. During the talk today, I will go over a few different cooling models that have been proposed to define plate tectonics on Earth and try to assess, given Earth's data, which of those are probable. So to begin, the easiest way for us to understand how Earth's interior has evolved is using simple energy balance models. We can do this. What we're doing with these is tracking the internal temperature of the mantle through time, and we're doing that based on the amount of heat that's produced within the interior, and tracking also the amount of heat that's lost from the interior. The amount of heat that's produced within the interior, we only consider the decay of radiogenic elements, and the amount of heat that's lost is based on the assumed convective processes that are going on. For Earth, we're going to make the simplifying assumption that plate tectonics has been operating since magma ocean solidification until present day. There have been other hypotheses put forward as to maybe transitions between different convective regimes, but we'll just brush that aside for this talk. An important value that I may be mentioning in a little while is the Uri ratio. That's one constraint we have on present day Earth, and that's going to be the ratio of heat that's generated within the planet to the amount of heat that's lost due to convective processes. The way that we scale that heat loss, in particular for plate tectonics, is based on the Rayleigh number. And that's just going to be a ratio of our driving forces to resisting forces, with our main driving force being buoyancy and main resisting being mantle viscosity, which itself is a function of temperature. And that's going to be raised to this power of beta. And that power of beta tends to be fairly important in what you actually choose that to be. It depends on how you actually formulate the dynamic system. So there are a range of different betas that have actually been proposed for Earth that have very different implications for how the system has evolved dynamically. The most classical value is a value of 0.3, and that assumes mantle viscosity is the primary resistor to plate tectonics. The way this works is that at higher temperatures, we assume that mantle viscosity is lower. Therefore, you can have faster overturns and cool the interior more quickly. Ways to actually reduce the efficiency of plate tectonic cooling is to incorporate the effects of plates. There's been a few different ways this has been done. One of the original ways of doing this was including the dissipation of energy due to plate bending and marginal strength. That brought the value of beta down to between 0 and 0.1. If you consider the size of plates, you can not bring the value as low because you have to also consider asthenosphere effects as well. You can also have the extreme opposite end member of what I described in terms of mantle viscosity being the main resistor, and say that plates are the primary resistor. In particular, you can say that melting effects on plate thickness are very important. So, for example, this would mean that at very high temperatures, you're creating very thick plates. And because you're creating those thick plates, they're harder to bend, they dissipate more energy, and that's going to make it more difficult to cool the mantle more efficiently. So what we choose to do here is incorporate all of these different models and test a range of beta values from negative 0.15 to 0.3, assuming that there's fuzzy boundaries between these different models. So what we'd like to understand is how mantle temperature has evolved through time. What we have on the horizontal axis here is Earth's history, where the present day is represented at 4.5 on the right, going back to 4.5 billion years ago. And then on the vertical axis, we have temperature. This is a typical evolutionary path that we see, this dark line here. This is our unperturbed solution. We also like to, first we sought to seek if these models were structurally stable. And to do so, we applied random perturbations throughout the evolution to simulate unmodeled effects. If the mean solution of multiple evolutions matched that of the unperturbed solution, we assume that the model was stable. Within this analysis, it also gives you some uncertainty bounds on that model, which we chose to go with a two sigma bounds as our uncertainty assessment. This helps us to evaluate these models against data. For instance, on the right, we see the present day distribution of temperatures for this particular model, one choice of beta, unique combination of initial conditions and parameter values. And we can see that for the given temperature constraints, you can have about 50% chance of success of matching those constraints. So what we did was we performed this analysis with a wide range of betas, a wide range of initial conditions and parameter values. And then, so that was around 1 million evolutions, and then compared that to different geologic constraints. This is where it ties into the uncertainty aspect. Even Earth, the planet that we know best, is still highly uncertain. Throughout Earth, we have measurements of what Earth's mantle temperature was throughout its history, with 0 being the present day and this being 4 billion years ago. You see that there's still a large spread in mantle temperatures. We use this as our paleo constraint, and even at present day, mantle temperatures are still only constrained to around 13 to 1400 degrees C. Another measure that we use as a constraint is the Urey ratio. As I discussed earlier, as a reminder, that's heat produced within, so the heat that's lost due to convective processes. The value for present day is thought to be between 0.2 to 0.5. However, if we consider the effects of continents, we can extend that upper boundary to around 0.7. So we can kind of think, what would the plate tectonic hypothesis be? Most likely hypothesis be if it's with continents or without. Performing all of those models using the geologic proxy data as constraints, we get these two distributions. These distributions are telling us for Earth which different cooling models are most probable. So the primary conclusion we reach, regardless if we take into account continents or not, is that all cooling models can satisfy Earth's geologic proxy data within uncertainty. So even for the planet that we know best, we cannot rule out any of the plate tectonic models. We can choose to take the best model if we want to, but we should probably do that with caution. Instead, we should probably test a wide range of models. One person phrased it to me as, maybe we could use this type of probability distribution as our prior in studies, and then connect that to other models, and that'll give us a distribution of the behaviors that we may see. So what I did, the results that I actually have to show you are different mantle cooling paths for Earth's history. You'll see here that we've gone from around magma solidification to present day, this red line, and extended the models out into the future. Each of these models here are able to match Earth constraints, and you see that they predict a vast array of behavior moving forward. And that's important because how the temperature cools directly relates to the amount of volatile cycling that's going on. So the volatile cycling can only continue as as melting is still occurring. For example, we can say that if mantle if melting shuts off at 1,000 degrees, we can predict a time when that melting will shut down. And giving all of Earth's data and all the different models, we can make a prediction that melting will shut down between, for the average solutions, in 1.5 billion years to it's still going on at 10 billion years, so double the age of the Earth. That's highly uncertain, not very promising. Doesn't really give us much information, but it's what we have to work with. Something else that we can do is take these internal temperatures. We can couple them to different types of models that allow us to track how much degassing is going on at mid-ocean ridges, how much regassing is going on at subduction zones. So to put it simply, we can track the amount of CO2 and water that's released into the atmosphere and taken back down. We didn't do a very complicated model here. All that we did was take and track the amount of, allow the velocities, what we did here was allow the velocities to influence how much CO2 was in the atmosphere, and then calculated from that the surface temperatures. We did this for the early Earth to show when, excuse me, just as a qualifier, these are some preliminary results. Now I'd like to emphasize the qualitative behavior of these rather than the absolutes. So what you're looking at here is when surface conditions first allow for liquid water to be present based on different cooling models. We see that if you go 4.5 billion years ago to almost 2 billion years ago, that's the wide range that we get. So even for the planet with the best data, we still have very uncertain knowledge about the evolution. What I would like to conclude with today is that we've shown a range of models put forth to describe plate tectonics, how those can account for Earth's geologic proxy data, and that these uncertainties in internal evolution lead to a range of times when Earth-like planets can enter and leave the classical habitable zone. And to tie it back to our first speaker, not of today, but of the first speaker we had, he made a quote. Stephen Kane said, "Uncertainties in solar system models translate directly into catastrophic uncertainties for exoplanets. Many questions remain for the solar system terrestrial planets, the answers of which will directly benefit exoplanets." As of right now, this is the answer that we have for you for Earth from a thermal evolution perspective. And I hope that you can take and use this and couple this to other models and get a true range of the uncertainties and the types of behaviors that we may actually see on exoplanets that are by definition Earth-like. Thank you.